There we go. Do a screen share. I'm actually going to jump into my there we go. In my notes, let me go back and see if I can find the quant notes we started last time. So here they are, just because I wanted to go back and just quickly review that titration problem that we were working on, because the idea is we wanted to continue with that problem today and see how far we get. When we'll definitely finish it, that won't be a problem. Everybody hear me okay before I get started?
Yep.
All right, excellent. By the way, I started looking over the kombucha alcohol analyses, and they look good. I mean, the standard curves for the most part look good. So, you know, you guys are doing a good job with that. So I think that experiment, given this is the first time we've actually run it with a lab, went quite well. So I'm actually really happy with both of the kombucha labs that we've done. So you guys are stepping up to the plate and doing good work with that. As far as next week in the lab, I guess I still have Monday to go over that with you, but I will later this week post the next lab, which is actually going to be a spectroscopy lab. So it's analysis of iron-ion using interaction of light with matter, which is spectroscopy. So we're going to use the Spec 20s, which some of you probably saw Kim and me bringing into the lab last night. All right, so other than that, we'll take a little break from homework. I'll try to figure out what the next homework assignment's going to be, but normally we don't have to have one of those every single time. So maybe 2 weeks out, we'll look at a new homework. So let's just go back over this EDTA titration problem that we started, just so we're all on the same page with it. So let's just restate the problem here real quick. So I'm just at the top of my screen here. So we got a 25 milliliter sample of 0.0376 molar calcium ion. I'm going to be titrating that with a 0.05 molar EDTA solution at pH 10. Okay. So the first thing we wanted to determine was the volume of the titrant needed to reach the equivalence point. As you guys know, the equivalence point is when the moles of the calcium have to be equal to the moles of the EDTA. Okay, so we can set this up with a mole bridge from the standpoint of the thing that we can get the moles of, which is the calcium. How come? Because I have a volume of the calcium and I've got a molarity of the calcium. And remember, volume times molarity gives us moles. Okay, so that takes us to moles of calcium, or millimoles in this case, since we're doing millimoles per milliliter. Okay. So once I've got that, I can go ahead and set up a mole bridge between the calcium and the EDTA, which I did, and we see it's a 1-to-1 mole ratio there. Once I have the millimoles of the EDTA, then I can use the molarity of the EDTA in that last step to calculate the volume of the EDTA that I need to reach the equivalence point. Okay, so this is really just nothing more than a bonding level stoichiometry problem. Okay, was everybody all right with number 1?
Yep.
Okay, good. And again, the reason I need to know that up front is because I need to know where I am in the titration so I know how to set the problem up. So normally we just need to know where that equivalence volume or equivalence point is. Then I know how to address the problem from there. All right, so part 2 is a situation where we're not quite at the equivalence point yet. So what I'm trying to do is calculate the free calcium ion concentration in solution when 14 mils of the 0.05 molar EDTA have been added. Now I know I'm prior to the equivalence point because problem 1 just told me I needed 18.8 mils of EDTA solution to get to the equivalence point. Okay, so 14 is less than 18.80, so I know I'm prior to the equivalence point here. Okay, so what I want to do is figure out how many moles or millimoles of each thing I've got in solution initially. Okay, so I can do that because in both cases, I've got a volume and a molarity. Remember, volume times molarity gives me moles, or in this case, millimoles. All right, so I can get my millimoles of calcium, all right, because that's what I started with. That number doesn't change. But what is changing is the volume of EDTA that I use. So in this case, I've got my 14 mils. I'm going to multiply by the molarity, and I get millimoles of EDTA. Now, given that we have a 1-to-1 mole relationship, we can see who the limiting reactant is, and we can see who the excess reactant is right off the bat, right? Because the stoichiometry is easy here. Obviously, I've got fewer millimoles of EDTA, so that's what I'm going to run out of. All right, so I'm going to show that using an ICF table. So here's kind of where we left off last time. So we needed an ICF table because we wrote the reaction for the formation of the complex, right? And that's governed by a KF, a formation constant. What do we know about KFs? KFs tend to be very large. In other words, way greater than 1. So if that's the situation, if I know I have a really large equilibrium constant, this is kind of like when we were dealing with acid-base chemistry or even with KSP type situations where if the equilibrium constant was really big, we could assume that the reaction goes 100% to the right. So I got a limiting reactant problem and I could use an ICF table. Now remember, with an ICF table, I can either put moles in there or I can put concentrations in there. Since I've already got moles in the form of millimoles, that's what I'm going to stick in there. Okay, so that makes sense to everybody. So let's take the calcium number and put it in for my initial. And that's millimoles. I'm just dragging it right down from the calculation that we just did. The EDTA is 0.7. Okay, what do I have initially of the calcium EDTA complex?
None.
Yeah, 0, big fat 0, haven't made any yet. Now, in the case of an ICF, we let the reaction go 100% to the right. So here's where the limiting reactant part comes into play. So we said the EDTA is the limiting reactant, so we're going to lose all of that. We're also going to lose an equivalent amount because of the stoichiometry of the calcium. Everybody okay with that? So how many millimoles of calcium EDTA complex am I going to make?
0.7000.
Good. Everybody all right with that? So now remember, we treat an ICF table like an ICE table. We just add down. So take the difference between the calciums and you get 0.24. Obviously, the EDTA is limiting, so we got none of that left. And we got 0.7000 millimoles of the calcium EDTA there. All right. So now, the next thing we have to think about is, well, actually, I don't even need to think about it here. So here's the question. Do I need an ICE table? Or am I pretty much almost done with this part? I'm almost done, right? Because the calcium is in excess, isn't it? Okay, and that's what I'm asked for. What's the concentration of the calcium ion in solution? So given that we're assuming the reaction is going 100% to the right, limiting reactant tells me that I'm going to have 0.2400 millimoles of calcium ion in there. Now I'm almost done, but what did I really ask for? Did I ask for millimoles of the calcium? No, I asked for the molar concentration. That's what the brackets up there represent. I want molar concentration of calcium ion. Okay, so how do I get molar concentration? What do I have to do?
Divide millimoles by milliliters.
Okay, which mils do I want? So what should I put in the denominator? You're right, milliliters need to go down there. Which milliliters need to go down there?
It'll be the 14.00 milliliters, right?
So let's see, we got 14.00 mils of the EDTA solution, right? Is that the only thing we got in there?
There's also the 25 milliliter original sample.
Yeah, we already have the calcium, because remember, we're doing this in the context now of what we've got in the pot during the titration. Okay, so what I really have to calculate is a V total. So the V total is going to be the 25 mils of the calcium ion plus the 14 mils of the EDTA. So the 25 was the calcium and the 14 was the EDTA, right? Now, we remember, especially we have Dr. Kagris, that we're not supposed to add volumes, right? Because volumes aren't additive because solutions are not ideal. But in titration problems like this, we're making a dilute homogeneous solution, so it's okay to actually do this. So when we do it, and it really is just an approximation, and that's all we need. But we all do this, 39.00 mils total. Okay. So that's what's going in the denominator. It's always V total. I'll just put solution here since it's the total solution. Okay, so now if I calculate my calcium ion that's left over, to my 4 sig figs, it turns out to be 6.154 times 10 to the minus third molar calcium. So the nice thing about this is the way this problem is set up. If I'm prior to the equivalence point, I don't need to do any equilibrium. I've just got really a limiting reactant problem to work. And again, that's because my KF is really, really big. Okay. All right, everybody good with that?
Yep.
All right, excellent. So let's go on to part 3 or C or whatever the heck I call it. I think I call it part 3 here. All right, so for prior to the equivalence point in part 2, where do you think I'm going to go in part 3?
After the equivalence point.
How about at the equivalence point? You're jumping ahead, that'll be part 4. Okay, so let's go back and think about our millimoles, right? And we can deduce this pretty easily. Let's go back up to part 2. Because remember, the calcium ion concentration doesn't change, does it? That's what's in the pot prior to the titration happening. So that's 0.9400 millimoles. So that's my initial concentration at my equivalence point as well. So remember, we're always going back to initial concentrations here. Okay, so if I'm at the equivalence point, what are my millimoles of my EDTA have to be?
(0.9400 millimoles).
Yeah, by definition, it has to be the same thing, right? That's the definition of equivalence point, right? It's where the moles of both things are equivalent to each other. In other words, I've added enough moles or millimoles of EDTA to fully react with all of the calcium that's there, and no more or no less, okay? All right, so the other thing that we have to think about here before we start really getting into this is we can go ahead and do an ICF table, and we're going to see how this all plays out. You can really do this in your head, but it's kind of nice just to do it just to make sure that we all understand what's happening. So let's just show the complex form. I mean, you kind of know the answer before you do it. And we know we can use a single arrow for this. I'll make the calcium EDTA. And that's what 2 minus now on the complex. So again, this goes 100% to the right. Okay, big K. We can do an ICF. Again, this is just proof positive. 0.9400, still putting millimoles down there. Who's my limiting reactant?
The EDTA.
Well, they're both limiting, right? So you could say either calcium or EDTA and it's going to be the same. That was a problem you couldn't, that was a question you can't get wrong, right? Both answers work. Okay, so you got 0 and 0. Okay, you had no calcium EDTA complex to begin with. You're going to make 0.9400 millimoles. Okay, add them up. So at the equivalence point, what have you got in solution? What you've got in
That's the
solution?
CA EDTA.
Yeah, it's just the complex. That's all you got in solution, right? Okay, so at this point, you could say, if you really wanted to, okay, there's no free calcium in the solution, right? But we can do better than that, okay? Because now it turns out there is some free calcium in solution. Where does the free calcium come from? There's only one place it can come from.
Calcium EDTA.
Yeah, it's coming from the dissociation of the calcium. Yeah, so I can run the reaction in reverse, basically. So now I'm going to treat it as a true equilibrium, right? Because if I do 1 over a big equilibrium constant, I'm going to get a small equilibrium constant. So the question now becomes, what is the equilibrium constant? I think we might have actually figured it out up top somewhere, if I remember correctly, when we were doing a, yeah, if you look here at this example that we did where we were talking about conditional KFs, we said we were at pH 10, and we said that 30% of the EDTA, so for the case of the calcium, right, which we did here, the KF was 10.65, which was the prefactor, the alpha factor we look up, times the KF that we get from the table. You get 4.5 times 10 to the 10th. Okay, so we actually, well, sorry about that. It's down here, 1.3 times 10 to the 10th. So there's the alpha multiplying by the KF. Sorry, I got ahead of myself. So 1.3 times 10 to the 10th is my conditional formation constant. So that's what we're going to use, right? Because we're at a pH of 10 and we can calculate the effective equilibrium constant. Okay, so that's the one we want. I thought we had done that one. All right, so I can say here that my KF is equal to 1.3 times 10 to the 10th. Now, remember, that goes with this reaction up there, doesn't it? Because I'm forming the complex. Now, for the reaction I have down below, how do I calculate the KF for that? It's conditional, so I'll put a prime there. How would I calculate my K for that?
You want the inverse.
Yeah, so I'm going to take 1 over the KF prime, okay, which is going to be a tiny number. All right, so let's go ahead and think about filling everything in. But what do I have to put in the ice tables? What populates ice tables?
Concentration.
Concentrations. I need molarities in there. Yes, indeed, I need molarities. So I got to go off to the side here and calculate some molarities, right? So what we have is the calcium EDTA in solution. So we know the calcium in EDTA, we know we can put 0 and 0 in there to begin with. But I do have an initial concentration of the calcium EDTA. So that's going to be the millimoles, right? Which we said was 0.9400. Divided by, oh, what do we have to divide it by? We need to be total, don't we? So what volumes did we have? Adding them up, it was 25.00 milliliters of the calcium. And then what do we have? 18.80 milliliters of the EDTA. Is that right?
That was 14.00.
Thank you. Let me just double check on that to get to the equivalence point all the way up.
It's 18. Yeah, it's 18.8.
18.80. Yeah, it comes from up here, right? Because we had to figure out what the volume of EDTA to get to the equivalence point was. So it's part A or part 1. That's what we need, 18.80. So don't forget about that number. Okay. Add them up and you get 43.80. So that's what goes in the denominator. It's always V total. And when you work this out, you get 0.02146 molar. Okay, so that's what's going to go in the I line under the calcium EDTA. Okay, everybody good with that? See where that came from? Okay, so which direction does this reaction have to run in my ice table, left or right?
Right.
got to go right because I got to make some calcium in EDTA. So that means I'm losing X on the left, make an X, and make an X. All right, so now we can plug it all into the law of mass action, can't we? So let's remind ourselves of what the law of mass action actually looks like. Okay, so it says that the KF primed, or it's actually 1 over the KF primed, right? And we can go and figure out what that number is here in just a little bit. All has to equal to equilibrium concentration of the calcium ion times equilibrium concentration of the EDTA. All divided by the calcium EDTA. You guys well into equilibrium and dynamics yet?
Yep.
Okay, good. So what do we say 1 over KF prime was? Let's go ahead and get a number for that. That's going to be 1 over 1.3 times 10 to the 10th. Just got that from upstairs. And that turns out to be 7.7 times 10 to the minus 11. So a really tiny equilibrium constant. That's what you expect. Okay, so let's get everything from the E line and stick it in. So calcium and EDTA are both X, so that's going to turn into X squared. Just subbing back in. 0.02146 minus X. And all that's equal to the 7.7 times 10 to the minus 11. Did I do that correctly? I think I got it all. So can I simplify this, guys? Make the math easy.
Yeah, it doesn't violate the 5% rule and you're going in the unfavored direction. So yeah, you can remove that additive X.
Yeah, we'll get rid of that bottom X. Very good. Okay. So if I do that, I'm going to end up with X squared is equal to 0.02146 times 7.7 times 10 to the minus 11th. Okay. And that actually turns out to be 1.65077 by my calculator times 10 to the minus 12th. But then to get to X, I need to take square root of both sides, right? So now X turns out to be 1.28. We can come back and get sig figs here in a minute. 48 times 10 to the minus 6 molar free calcium. How many sig figs do we need, guys? I think it looks like 2, doesn't it? So basically it's about 1.3 times 10 to the minus 6 molar calcium. So yeah, I've got a little bit of calcium ion in there, guys. Now here's the question I might pose to you. Why did I not bother to do this in part 2 when we were before the equivalence point? Why did I just let that be a limiting reactant calculation and not really worry about the calcium EDTA redissociating to give me some calcium ion back? Why did I not bother to do that?
Because the KF was so big.
Well, yeah, that's basically it. So essentially what's going to happen is notice that I've got some calcium in there and it's what, 6.15 times 10 to the minus 3rd molar. Okay, so let's say we went and figured out that we had a little tiny bit coming back through the redissociation of the calcium EDTA. I could do that if I wanted to, but then I'd have to kind of add that back to what I've already got. So let's say I got something on the order of like 10 to the minus 6 or something like that. Does that really effectively add to 10 to the minus 3rd in a meaningful way? No, it really doesn't. So in that sense, it's there, but we just don't need to worry about it. It's too small a quantity to even bother calculating. But by the time you get to part 3, where we're truly at the equivalence point, notice that you don't have any free calcium left in the ICF table. So now you really do have to let the reaction go back in reverse, okay, to generate a little bit of calcium ion. Does that make sense?
Yeah.
All right, good. So let's look at part 4. So if part 3 was at the equivalence point, then part 4 ought to be beyond the equivalence point, right? So now we'll put 25 mils of the EDTA in there. Okay, so now we're beyond it. So let's again assess our millimoles of things so we can kind of just see where we are. So the millimoles of the calcium, remember, never changes. That's a fixed quantity. So that was the 0.94. Once you calculate that once, you've got it for the whole problem. But now we have to recalculate your millimoles of EDTA, because that does change as we add more and more of it to the solution, right? So that's the volume of it, which is 25 mils that I put in there. Times the molarity of it, that's 0.05. Millimoles of EDTA per mil. Okay, so mils cancel with mils, and I'm going to end up there with 1.250 millimoles. Of my EDTA. I'll go ahead and put the 4 minus in there just to be proper about it. All right, so now let's do an ICF table again. Because again, the calcium ion that's there has to react with the EDTA ion that's there. Okay, so I've got calcium 2 plus EDTA 2 minus, 4 minus, sorry. Go 100% because I got a big K. And I'll make my calcium EDTA again. All right, ICF. So we can treat it like a limiting reactant problem. Since it's an ICF, I'm going to put millimoles in there. So calcium 0.9400 millimoles, and EDTA we just figured out was 1.250, right? Yep, that looks good. Do I have any calcium EDTA in there? No, I don't. All right, so who's now? Who am I going to run out of?
There for a minute.
What's that?
You cut out there for a minute. Could you repeat what you
Yeah, I
said?
sure can. Yeah. Who's limiting now? Is it the calcium or the EDTA?
The calcium.
Yeah. I got to make the same amount on the right. All right, so it looks like for the calcium, I have none of that left. 1.250 minus the 0.940 is 0.310. Okay, so that's the millimoles of EDTA I have left over. And I've still got 0.9400 millimoles of calcium EDTA in. All right, so again, how am I going to make free calcium ion in this case? How am I going to get some calcium ion back?
With the Ca EDTA.
Yeah, I got to let that dissociate. So I'm going to flip the reaction again, just like we did in part 3. It's an equilibrium now. We've already figured the K out for it. So I'm going to make some calcium ion. I'm going to make some EDTA 4 minus out of this. Okay, now I want an ice table, right? Okay, but what goes into an ice table, guys?
Polarity, concentration.
Molarities. Yeah, we need molar concentration. So what's my V total now? I think it's 25 and 25, right? All right, so what am I going to do? Well, I'm going to now divide my molarities by that. right? So for example, if I want to get the EDTA concentration, we'll just do that one to show you how we got it. Okay, it's going to be the 0.310 millimoles of it divided by my 50 mils. Okay, and that should turn out to be, let's see, that's the calcium. What was that? Oh, that's the EDTA. Check me there, 0.00620. Is that what you get?
Yeah.
Thanks. That's molarity. Okay, now I'll leave the calcium EDTA for you guys to do. So when we plug everything in, the calcium EDTA turns out to be 0.01880 molar. And the EDTA, there's no calcium in there, right? Because that's limiting. And this guy, the EDTA is 0.00620 molar. Okay, does that look right? So which way is this reaction got to go, guys?
To the left.
Can it go to the left?
Oh, no, never mind. To the right.
Yeah, it can't go to the left because there's no calcium. So we have to go right. Got to make some calcium. That's always an easy way to figure it out. Look for anything that has a 0 concentration in it. You know the reaction has to go in that direction to make some of it. So I got minus X, I got X and X. That's a plus X over there. All right, now we're going to put everything back in the law of mass action, right? So now I need to have that 90K value that I had, which was, we'll just remind ourselves, that was 1 over the KF primed, okay? And we calculated that before. That turned out to be 7.7 times 10 to the minus 11th. Okay, products over reactants. So let's see, I need the X there for the calcium. I need 0.00620 plus X up there for the EDTA. Then I need the complex in the bottom. That's 0.01880 minus X, right? All right, that thing just looks ugly, doesn't it? Can I simplify it? Make the math easy.
Yep.
What should you do? Show me some X or X's you can get rid of.
You should be able to get rid of the X that's subtracted to 0.0188.
Okay, I agree. See any other X's you can get rid of?
Connected to the 0.00620.
Yeah, that's an additive X, so we can get rid of that one too. Okay, so now this makes the math really nice and easy because now what I've got is X times 0.00620 divided by 0.01880, right? And that's all equal to that really tiny K of 7.7 times 10 to the minus 11th, right? So that's easy to solve now. Everybody can solve that for X. And when you do that, we end up getting 2.3 times 10 to the minus 10th. And that's molar calcium. Now it's interesting to note that that should be a lower concentration of calcium ion than what I had in step 3. So what did we have up in step 3? We had about 1.3 times 10 to the minus 6. Now we're down at 2.3 times 10 to the minus 10th. Okay, so based on your knowledge of equilibrium, why did the concentration of calcium get that much smaller?
Because it was a limiting reactant this time, right?
Well, we always have a limiting reactant, right? Look at the reaction I have at the top here.
Was it because there was so much more EDTA?
Yeah, look at that. You got EDTA in there to begin with, right? Which you didn't have in step 3, right? In step 3, notice in the ICE table, you didn't have any EDTA there. So remember, that's common ion effect, Le Chatelier's principle, isn't it? Which we talked about. So if I already got some EDTA in there, even though I'm using the same equilibrium constant, okay, I'm going to get less dissociation because I'm now dissociating the complex in the presence of a common ion, which is the EDTA 4 minus. In other words, I've added a product. And if I add a product, what does the Chatelier's principle say? Well, it says that that's going to push a reaction back in the opposite direction. And that's exactly what we see. Okay, so basically what we've gone through here, guys, is pretty much a full-on titration problem. So the nice thing about these kinds of problems is once you've seen the setup on a titration problem, they all work the same way. So for example, when you get to dynamics and you start getting heavily into acid-base chemistry, which we've already kind of covered in this course, one of the things that you're going to do is you're going to do titration problems like this in the context of acid-base, okay? But everything we showed you here in terms of the setup applies, okay? There's really nothing different about it. Now, the interesting thing about it, going back to stuff that we kind of did before, was that you guys might remember that post-lab question on the kombucha acid lab, where you kind of had to pick off an equivalence volume, and then you had to pick off like a pH from one of your plots, and then you had to generate like an ice table to figure out what the Ka for acetic acid was. This is kind of the approach you had to take. So it actually would have been useful to have seen a problem like this prior to that. And in that situation, I had to really go back and think about it because that problem kind of caught me by surprise. I totally forgot it was in there because Dr. Kagris kind of stuck it in there. And then a couple of you guys asked about it. And I was like, whoa, wait a minute, I got to rethink this problem here. I got thinking about it. It's like, yeah, it's just a titration problem when you really get down to it, because where are you in the curve at the equivalence point? Well, you're at that equivalence volume. You're at the equivalence point where the acid and the base moles are equal to each other, right? And that's the definition of it. But then the question is, it's kind of like you have to move from that ICF table to the ICE table. And you have to ask yourself, well, what's really in there? Okay, and I think I was having this conversation with John because he was like the first person who asked me about it. And he says, well, you got the acetate ion in there, right? And that's exactly right. Because when you're at the equivalence point, what's in solution? Okay, it's not the acid anymore, it's the conjugate base. You've converted 100% of the weak acid to its conjugate base. Okay, so now what you're really looking at is the conjugate base dissociating in solution. Okay, so notice that when you went back and picked that pH off at the equivalence point, was it an acidic pH or a basic pH? John will be able to tell me.
Basic.
It was a base because you had the conjugate base dissociating in solution. So really what you're doing is you're back calculating hydroxide ion in solution. So the way John went about doing it in his problem was he ended up calculating a KB from the perspective of the dissociation of the weak base. And then if you got a KB, you can convert that back to a Ka for the original acid. So I think that's exactly what Dr. Kagris intended for you to do. Now there's another way you could do it. Okay, and I think Ian did it this way, is you could actually get the equivalence volume, and that tells you how much acid you had in there. Okay, so you have an initial concentration of the acid after dilution. And then what Ian did, which also works, is you could go back and then calculate your initial, or just pull off your initial pH before you added any base to it, because that's indicative of the amount of hydronium ion you're getting from the dissociation of the weak acid before you titrate it. So really either one of those approaches would get you to the right place. So to be honest, one of these titration problems would have been really, really helpful to have seen prior to that. So that's something I might introduce if I keep that question in there next year. But the point is, it was a really interesting thought process for a lot of you guys, and you guys actually did pretty well with it, I have to admit. So, you know, it was an interesting thought process, and that's what Dr. Kagris is always after when he's doing these kinds of questions. So I just thought it would be kind of fun to revisit that and just say, okay, that's kind of how you set it up. And there were actually a couple of ways you could have done it. All right, that takes care of that. So I don't think I want to start a new topic today. I've actually got a lab I have to run tonight. So I'm content to leave it be with 10 minutes. So are you guys okay with being let out early, slightly early on a pretty day?
Yep.
You
That's
don't feel
perfect.
like you don't feel like you're getting robbed of your 10 minutes worth here? Nobody feels robbed?
Nope.
Not this
All right.
time. It's too nice out.
Yeah, that's what I'm saying. I guess if we're snowing or something, we had nothing better to do, I'd say, okay, we make something up. But yep, I think for now, this is probably good. So that said, see you guys on Monday, and I'll get that new lab out to you guys. Don't worry about any homework. We'll probably assign some next week once I figure out what I want it on. And we'll go from there. Okay, any questions, comments, concerns?
No, sir.
All right, folks, enjoy the rest of the beautiful day, and we'll see you on Monday.
Have a good one.
You see ya.
Hey, you too.